Hi, thanks for tuning in. My name's Hillman. I'm at Princeton University. First, I'd like to thank Enrico and Guy for organizing this meeting. Today, I'm going to be talking about the application of the symbol, a basic piece of technology in studying transcendental functions, to studying the de Sitter wave function. So first, some general motivation and background. Generically, we already see at tree level that perturbative contributions to the de Sitter wave function are rational functions times polylogs. So this is already more analytic complexity than we're used to in flat space, where we only expect poles at tree level. Additionally, recent work has demonstrated the power of conformally coupled correlators as building blocks for more general correlators, where the more general ones can be obtained by the application of weight-shifting operators or spin-raising operators to a conformally coupled seed. If we focus specifically on conformally coupled scalars exchanging a conformally coupled scalar, then these correlators are going to be pure polylogs of uniform weight. This motivates the use of the symbol for the study of these pure polylogarithms. And the symbol is a computational halfway place between having a form and an integration cycle, and then having the full function, where the symbol places all the analytic structure on display. So the main result regards what I call symbol recursion, specifically applying to phi cube theory for conformally coupled scalars in DS4. Which can be used to generate more general correlators via the application of weight-shifting operators and spin-raising operators, though not the full menu of general massive exchange. So the benefits of this are that the symbol provides a conceptually clear and simple construction and computational simplicity over performing just the time integrals from scratch. And this allows us to explore the analytic structure of endpoint DS correlators with greater simplicity. So with that motivation, now we'll dive into just the basics of symbology. So first, definition of the symbol. Given the transcendental function of weight n, which we denote by Fn, we can recursively define the symbol in the following way. The differential of this function will be a sum of transcendental functions of weight 1 less times d logs of rational functions Ri. And the symbol is defined as such, where the rightmost entry will be the argument of those d logs, and we recursively define the symbol of those transcendental functions as what appears on the left. So given a function successively taking differentials, or given an integral representation and successively taking differentials, you can build the symbol of a transcendental function. So in particular, from this definition, we see that the symbol manifestly records the differential equations that this function obeys. But additionally, the symbol also records the logarithmic singularities of Fn of all codimension. So the differential structure is sequentially contained read from right to left, as the rightmost entry is the first d log when you take just a first order differential of the function, but the leading singularities will be found from left to right. And this could be seen from standard arguments of the branch cut of log of z appearing as an integral of dz over z, and just more complicated nested cases thereof. So now we can see how the symbol relates to these functions in action, in particular by focusing on an important class of transcendental functions, which are the classical polylogarithms. So they are defined in the following way, as iterated integrals. The first polylog, Li1 of z, is just log minus log of 1 minus z. And then Li n is defined in the following way, where we integrate Li n minus 1 against d log of t. So it's pretty straightforward to see that the symbol is going to be minus 1 minus z, and then just successive z's, n minus 1 of these, for Li n of z. And so we can confirm that the 1 minus z is capturing the branch point in the complex plane. And then we can use this symbol to just confirm some basic facts that we already knew. So for 1, taking the differential, we see that this logarithmic derivative gives us Li n minus 1 of z. But additionally, we can see that the discontinuity across this cut beginning at z equals 1 is going to give us just the symbol with the n minus 1 z's. So that's totally symmetric, and that's readily identified as the symbol for the following function, log to the n minus 1 of z over n minus 1 factorial. So this wasn't anything deep or profound that we learned, but we can see how the symbol neatly captures this information about the analytic structure. And a small comment is in order, which is that the symbol will only uniquely capture the highest weight part of a function, as it misses functions of lower weight times transcendental numbers. And that can be seen from the d-log definition, which we presented, as eventually you'll take the differential of a transcendental number, for example, at weight 3, pi squared over 6 log z, and so the symbol does not capture that information. So here we'll just compile a summary of the basic symbol rules, which will be of value to us. So you can take linear combinations of symbol words, and they are combined by log rules. Given the definition, it's clear why we should imagine each of these entries as really being having a log there. So ABC would combine as the difference of ABC and ADC as A B over D C. Additionally, we can take the symbol of a product of transcendental functions, and the symbol of a product of functions is the shuffle product of their symbols, where the shuffle product of two symbol words is formed by taking all ways of interlacing the letters between the two words while preserving the internal order of the letters within each word. Where here the letter A is the first letter in this word A tensor B. We denote the shuffle product with this symbol. And here we've expanded the shuffle product of A tensor B with C tensor D. So we see that we get these 6 terms, but A never passes B and C never passes D. But otherwise we have all ways of ordering the letters. So now we're equipped to discuss symbol recursion. So this result is naturally phrased as a statement about the locations of the singularities of a contribution to the ds wave function, and then the factorization properties of the discontinuities of a given Feynman graph contributing to the de Sitter wave function. So for notational simplicity, we will truncate the edges running to the boundary. So this and this will be truncated. So this 4-point contribution will just be a dumbbell. And each vertex in a graph, therefore, can carry some amount of energy propagating to late time. So the statement about the location of the branch points of a contribution to the ds wave function is that if we consider a contribution fg associated with some general graph g, then the branch points of this contribution correspond to connected subgraphs, lowercase g, so this connected subgraph, and the discontinuity occurs, the branch point is located where Eg, the energy that we define here, goes to 0. These are referred to as partial energy singularities, and this energy is the sum of all vertex energies contained in lowercase g, plus the edge energies which are cut by enclosing this connected subgraph g. So the half edges contained in lowercase g. So this comprises all branch points of the contribution fg. And we note that we will denote complementary connected subgraphs to the graph lowercase g as g bar I. So now we're interested in the behavior of the function around one of these singularities, or in particular what the discontinuities across these branch cuts are. So the key result can be described first after just a brief bit of notation, which is that if we have a subgraph G with half edges on the outside, then we will denote the contribution corresponding to this graph as Fg with a sign pattern as a superscript, where the sign pattern denotes whether the edge energy is absorbed with a plus sign or a minus sign. And the absorption is just that the energy is added to the vertex energy on the vertex where this edge terminates. Okay. So given this bit of notation, we have that the discontinuity associated with a subgraph G, a connected subgraph, which occurs across the cut, beginning at the branch point when Eg goes to 0, is equal to the total energy discontinuity of Fg, the contribution from just that subgraph G with all plus signs, times the product over all of the complementary subgraphs of this subgraph G, where within each product here, we sum over all ways of absorbing either positive or negative energy on each of the half edges, with the sign being -1 to the number of plus signs on these half edges. So that's a fact about the factorization properties across these branch cuts. And it's more clearly depicted graphically, if that was a bit confusing. So we could enclose this subgraph as the subgraph lowercase g, and then the dashed lines are depicting the taking of a discontinuity corresponding to that subgraph. So then we say that this discontinuity is equal to the total energy discontinuity of this graph absorbing positive energy times the contribution from this complementary graph absorbing negative energy minus the case where it absorbs positive energy. We could look at another case where here we have the discontinuity associated with this subgraph. So then we get the total energy discontinuity associated with this graph, absorbing positive energy on both half edges. And then we sum over all ways of absorbing either positive or negative energy for the two half edges going into the complementary subgraph. And so this gives us 4 terms with this appropriate sign pattern. So To get any utility out of this recursively, we need one more fact, which is that the E-total singularity, the discontinuity across the E-total branch cut, is equal to minus the sum of the discontinuities across all other cuts. So this is guaranteed by good behavior of the rational integrands at infinity and a residue theorem. This is sort of analogous to BCFW and its utility coming from the good high energy behavior of Yang-Mills and gravity, say. So this fact now gives us immediate utility to the factorization property stated above, because now we're capable of recursing downward. So tying things together, we're able to take this statement about the discontinuities, because recall that the first argument in the symbol, when it vanishes, that is the leading branch point of the function, or one of, if the symbol of the function is a sum of words. So now we can convert this into a statement about the symbol of the function corresponding to the contribution from a graph G, and the symbol takes the following form. So all of the discontinuities, the branch points, occur with the partial energy singularities, e.g. So we sum over all connected subgraphs, lowercase g. The fact about the E-total singularity lets us simply divide, recalling the log rules of combining symbol words. And what we get in the rest of the symbol word is a shuffle product, as the product over functions descends to a shuffle product over symbols. We get a shuffle product over the complementary subgraphs, G bar I, where we retain the same sign structure for absorption of a positive or negative half-edge energy, and we have the symbol of the contribution from the complementary subgraph G bar I. So with this expression, we can now build up symbols for general graphs G. So we will now illustrate this for the 4-point contribution. So the truncated graph corresponding to the 4-point contribution, we write it again here. So the bottom of this recursion is always going to be this graph, perhaps absorbing half edges. And this graph corresponds, if we reintroduce the external particles, to this, and that's just a log. And the symbol is just the energy running to the boundary. So this will always be the bottom of the recursion. And now we can simply build up the answer, knowing that this root case is a log. So there are two discontinuities that contribute to the construction of the symbol in this case. There are only two interesting connected subgraphs that aren't the graph itself. So first we circle this left vertex, and that's x1, the energy, vertex energy there, plus the half edge, divided by the total energy. And now the two cases for the complementary subgraph are subtracting the half edge and then adding the half edge. The other term is just symmetrizing in x1 and x2. And then the symbol of the function is the following. We just add the two terms. So this is the symbol, and it's actually readily integrated in this case, only at weight 2. So we'll introduce the variables u1, 2. And in these variables, it's easy to see that the symbol takes the following form. And if we recall the symbol that we computed for our classical polylogarithms, we recognize this will just be the Lie2 part, and then here we have symmetrized there and there are just a product of Lie1s. And so the contribution for this 4-point function takes the following form, where here we account for the contributions of lower transcendentality times transcendental numbers that we might be missing. And this will need to be fixed by a boundary condition. And so we have a boundary condition at our disposal. When the exchanged edge energy goes to 0, the contribution should vanish as the propagator vanishes. In this limit, we also see that u2 is actually 1 minus u1, and the function takes the following form. And by an Euler identity, this is actually equal to zeta of 2, and so the contribution of lower transcendentality that the symbol misses is minus zeta of 2. And so this fixes the function, and this is the familiar result for the conformally coupled scalars exchanging a conformally coupled scalar. So this produces the basic building block that can be used to generate graviton exchange, massless spin 1 exchange, and other things using weight shifting and spin raising operators, and in fact has been used in the various papers by Guy and Dan and Hayden and friends to compute these various observables. So now we can discuss the general case. In general, it's quite easy, in particular using Claude Dur's polylog tools package, to put the symbol recursion on a computer and produce the symbol for an arbitrary endpoint function. Now, explicit integration becomes intractable beyond 5 points. The explicit answer at 5 points is provided in the paper, symbol recursion for the ds wave function, where it's also shown that it requires going beyond classical polylogarithms beyond 5 points due to a theorem of Sasha Goncharov. So this doesn't make us dead in the water, though. The symbol still has great utility as it contains information about the differential equations that the function obeys and can help us get useful series solutions. And it's readily acted on by differential operators, such as the weight shifting operators that have proven so useful lately. And additionally, it contains all of the rational data. So a correlator, which is just a rational function that can be obtained by applying suitable differential operators to the conformally coupled external particles exchanging conformally coupled scalars. The symbol already has this information with no extra integration needed. So now we can discuss just the general outlook and some opportunities and summarize what we've seen so far. The symbol can be uniquely constructed with the statement of the types of singularities that we allow, the location of these singularities, and the factorization properties of the answer at these singularities. And this is the usual on-shell picture, simply with more complicated analytic structure in this case. But with this tool, we need no longer make any reference for this particular class of correlators or wave function contributions to time integrals or anything else. We can simply perform the symbol recursion and we have the endpoint answer. As we said, the rational correlators, which can be deduced from conformally coupled scalars exchanging conformally coupled scalars, should be readily attainable just from the symbol itself. It needs no integration. This could be at arbitrary points. And so it would be interesting to look at something like Yang-Mills, something like graviton exchange, external gravitons, and see if such differential operators can be constructed and if they inherit any of the structure of symbol recursion, or perhaps something nicer, analogous to a BCFW for cosmology. And so a general point to stress is that conformally coupled external scalars exchanging conformally coupled scalars, this is the highest transcendental weight function at a given number of external points. And noting that you can only generate transcendentality via integration, but you can knock down transcendentality simply by applying differential operators, can we hope that simply from the conformally coupled answer, we can descend to, say, any integer conformal dimension for external or exchange with the application of suitable differential operators? And another interesting question might be, what does the symbol recursion say in Mellon space? What form does it take? So thank you again for tuning in, and I look forward to chatting with you at the conference.